Okay, this turned out to be more number of podcasts than I expected, but that's okay. I think we'll be able to conclude with this podcast. I cannot see my cursor for some reason. Oh, come on, don't do this. Okay, right, here we are. Advancing science. So finally, there is no doubt, as exemplified in this perspective, that modern machine learning methods greatly improve classification and prediction skills. This alone has great value. Yet, beyond statistical prediction, the question is how data-driven approaches can improve fundamental scientific understanding, given that the outcome of complex statistical models, in particular, is often hard to interpret. If you just use data-driven AI deep learning output, it can be hard to interpret. Sometimes you even get papers to review that say we got good results, but we don't know why. We cannot interpret it right now. One basic answer is that observations have almost always been the basis for scientific progress. For example, the Copernican discoveries were enabled by the precise observations of planetary trajectories to infer and test the laws governing them. Now, although the general cycle of exploration, hypothesis generation and testing remains the same, modern data-driven science and machine learning can extract arbitrarily complex patterns in observational data to challenge complex theories and Earth system models, as we saw in the supplementary figure 3. Data-driven models, theory models, and how they can connect to hypothesis building and redefining hypotheses and so on. For instance, spatially explicit global data-driven estimates of photosynthesis based on machine learning have indicated an overestimation of photosynthesis in the tropical rainforest by climate models. This mismatch has led scientists to develop hypotheses that enable a better description of the radiative transfer in vegetation canopies, which has led to better photosynthesis estimates in other regions and better consistency with leaf level observations. So that's advance in understanding and modeling. And output. Related data-driven carbon cycle estimates have enabled the calibration of vegetation models and helped to explain the conundrum of increasing seasonal amplitude of CO2 concentration at high latitudes, which according to these results is caused by vegetation being more vigorous in the high latitudes. You have to go and understand what that means, but there is a more recent paper which used palm radiocarbon from the 1950s to look at current levels in actual vegetation data and argue that the models are keeping the carbon in vegetation for too long, that in reality carbon overturns much faster. This could obviously have a lot of implications for carbon cycle itself, right? So what are the conclusions then? Earth sciences need to process large and rapidly increasing amounts of data to provide more accurate, less uncertain and physically consistent inferences in the form of prediction, modeling and understanding the complex Earth system. Machine learning in general and deep learning in particular offer promising tools to build new data-driven models for components of the Earth system and thus to build our understanding of Earth. Challenges specific to the Earth system will further stimulate the development of methodologies, and we have 4 recommendations as follows. Who doesn't love bullet points, right? Recognition of the particularities of the data. Multi-source, multi-scale, high-dimensional, complex spatio-temporal relations, including non-trivial and lagged long-distance relations like teleconnections between variables, need to be adequately modeled. Deep learning is well positioned to address these data challenges, and network architecture and algorithms need to be developed to produce approaches that address both spatial and temporal context at different scales, as we saw in this figure here. Okay. Second one, plausibility and interpretability of inferences. Models should not only be accurate but also credible, incorporating the physics governing the Earth system. Wide adoption of machine learning in the earth sciences will be facilitated if models become more transparent and interpretable. Their parameters and features feature rankings should have a minimal physical interpretation, and the model should be reducible to or explainable by a set of rules, descriptors, and relations. Uncertainty estimation. Every time you write a proposal or a paper, reviewers always ask for uncertainty estimates. Models should define their confidence and credibility. Bayesian and probabilistic inference should be integrated into models because such inferences allow for explicit representation and propagation of uncertainties, especially when you have a complex model like the Earth system. In addition, identifying and treating extrapolation is a priority. And finally, testing against complex physical models. The spatial and temporal prediction ability of machine learning should be at least consistent with the patterns observed in physical models. Therefore, we recommend testing the performance of machine learning methods against synthetic data derived from physical models of the Earth system. For instance, the models in figure 4b and c, where we looked at the temperature and photosynthesis and predicted future temperature field. Okay. So 4b and c, which are applied to real data, should be tested across a broad range of assimilated dynamic. Let me read that again. Completely mucked it up. For instance, the models in figure 4b and C, which are applied to real data, should be tested across a broad range of dynamics as simulated by complex physical models. This is of particular relevance in conditions of limited training data and to assess extrapolation issues. But be careful here, because we are saying AI can be used with data for improving parameters or replacing submodels and do hybrid modeling to improve the outputs or predictions, simulations, and so on. But here we are saying AI/ML should itself be tested against models. Models have biases and uncertainties, so it's not a very linear process, as you can imagine. Overall, we suggest that future models should integrate process-based and machine learning approaches. Data-driven machine learning approaches to geoscientific research will not replace physical modeling, but strongly complement and enrich it. Specifically, we envision various synergies between physical and data-driven models, with the ultimate goal of hybrid modeling approaches. These should obey physical laws, feature a conceptualized and thus interpretable structure, and at the same time be fully data adaptive where theory is weak. Importantly, machine learning research will benefit from plausible physically based relationships derived from natural sciences. Among others, two major Earth system challenges in which little progress has been made recently: the parameterization of atmospheric convection and description of the spatio-temporal dependency of ecosystems on climate and interacting geofactors could be addressed using the hybrid approaches discussed here. Tempting and will be tried by somebody, is already being tried in various forms, but not explicitly to show that deep learning can improve hybrid coupled models. There is no functional hybrid coupled model yet. European Center for Medium Range Weather Forecasting is taking AI based approach to forecasting, so you have to go and see the details of what they are doing. Are they replacing submodels? Everybody is doing improving of parameterizations with AI approaches now. This has become part of the way models are improved and developed. Everybody is doing some AI forecasting, at least downscaling that I mentioned before that we are doing for Mumbai flood forecasting, and replacing of submodels. As I said, radiative transfer models have been replaced. I think full AI models to save a lot of time, or you have to check it, maybe it's a blended submodel, so it's not a fully coupled climate model with deep learning model or a ML model, but it's a combination of submodels, not replaced, somehow blended, and the full model still can be interpreted as mainly a dynamical model. So this will take various shapes as we go along, and as data keeps interpreting, the other thing to remember is that let's say we get very good at advancing process understanding with deep learning with more and more data, and the models get better and the models get very high resolution, something like 1 kilometer. I have podcasts on K-scale modeling because there is an argument by a group like Tim Palmer and Julius Lingo and Bjorn Stevens that the IPCC class models, which are run at, let's say, 50 kilometer or tens of kilometer scale, are simply not ever going to give skillful information at the scales at which decisions have to be made. So they say only way is to go to 1 kilometer scale global models. What's the point? The point is these models will produce so much output, so many petabytes, that they can only be analyzed with AI as well. Okay, so last mile use of the forecasts even with coarse models or interpretations of high resolution models will all be about AI. So that goes back to the figure we looked at, figure 1, where we said velocity, veracity, and variety, and what was the fourth V? Let's look at it. Dun-ta-da. We might as well conclude it properly. So we said volume, velocity, variety, and veracity, and we have to reduce it to patterns and knowledge that are small and digestible, real time for some applications, integrated across disciplines, and confidence robustness for users. So this is the perspective that this paper presented. Okay, so let me leave it here. Definitely go back and read the paper and look at all the citations. Tremendously rich in terms of the citations. Okay, see you.